information on this really interesting integrated applications of this. It raises a lot of questions on potential use and acceptance, and all the problems come in with new introductions. Our next speaker and our last speaker is Dr. Julien Ryckaert, who joined the Inter-University Microelectronics Center in Louvain, Belgium, in 2000 as a RF designer, and who worked on low power, low data rate, ultra-wideband receiver architectures from 2000 until last year. And he completed his PhD in this project. Dr. Ryckaert is now heading a project on RF transceiver architecture for cognitive radio in deep submicron technologies. Dr. Ryckaert. This advances the slides.
The green one.
And the green one, and that is the pointer.
Okay. Thank you, Mr. Chairman. And I'm the lucky last presenter, so I hope I'm going to keep the entertainment with my presentation. So I'm from the wireless community. Okay, my presentation follows nicely, obviously, the presentation of Stuart, and I'm going to detail a little bit the work that we've been doing on the radio implementation in those sensor nodes. One thing, so I'm going to take the wireless community perspective. It's a little bit different from a lot of the presentations I've seen here, but maybe that's going to be a little bit interesting for you, I hope. What we've been trying to do is we've figured out that in the sensor node, one of the major, there are many challenges, but one of the major challenges is the design of the radio. And the big problem there is the power consumption of the radio. So we've tried to figure out some techniques that allow us to break the power consumption gap and get to the scavenged energy figures that were shown by Seward. And we figured out that there is an interesting technology that is called ultra-wideband communication, which is a recent technology that allows good power consumption figures for the radio in the context of sensor networks. Now, I've seen many visionary presentations, and in the wireless community, we also have visions. And actually, I will broaden a little bit the scope outside only healthcare applications, but in the wireless community, we have a vision that is called the ambient intelligence. And what it means, and I will just refer a sentence from Fred Brookhorst at Philips Research, who had a keynote speech at ICCC in 2002. And he defined ambient intelligence as an environment where technology is embedded and hidden in the background. And what it basically means is that everything, all your surrounding, the air, every device, electrical or not, will be continuously monitored by different sensors, such that you will be able to interact with the environment. So the environment is going to be intelligent, and you're going to be able to interact with that environment. Now, that's the kind of vision that we have there. Now, there are different applications, scenarios, where you can see that ambient intelligence happening. Now, obviously, we've been talking a lot about healthcare. I'm not going to detail because there was a lot of presentations about that, but there are many other types of applications where you can see that ambient intelligence being applied, like in fitness. Stewart also said a few things about that. In industrial applications like agriculture, you could monitor the environment, the plantations, the workers, and decide, for instance, what is the best time to harvest. In domotics, that's also an obvious application for those sensor networks. So now sensor networks will be used in many, many different types of applications. Now, the technology that is necessary is obviously a network of sensors that will be communicating with each other. That information will then be collected and sent through to the global network, being, for instance, the internet network, through different more classical wireless communication systems like Wi-Fi or cellular communication systems. So that vision requires the deployment of those sensors. So if you look at one of those sensors, that's an example of a basic sensor. So it has different functionalities. Stewart talked a little bit about that. So you have the energy scavenging, you have the sensing part, obviously, you have some processing, and the radio communication. And that's what I'm going to talk about today. So in the radio communication, we have three major challenges. First, that is the power consumption, and that's probably the most important one. We need autonomy that are on the orders of years. And if you look at radio communication systems today, they cannot achieve that type of years of autonomy. There is also obviously the size that should be non-invasive. There's the cost. They want them to be disposable. So these are major challenges. Now, what do we have at our advantage in the communication to reduce the power consumption? What can we trade to reduce the power consumption? And that is the communication performance that is expected from those radio devices. We're talking about data rates that need to be to an absolute maximum of 100 kilobits per second. Right? So the big question was, how can we try to trade power consumption for performance? So you would say, if I decrease the performance of my radio, obviously I would hope that my power consumption is going to decrease too. But there is a question mark there. And I'm going to detail a little bit why there's a question mark and not yet an answer. And the thing is, what you need to optimize is not the power consumption in the end, it's the energy. What the sensors have a certain capacity, a certain amount of energy that they can use. And basically, what you want to optimize is how much energy it costs you to transfer a bit of information. And to get that metric, basically what you have to do is simply divide the power consumption of your radio by the data rate. And you get a metric which is called the energy per bit. Now, obviously, you see that if power consumption decreases, your energy per bit would decrease. But what is not nice is that if the data rate increases, the energy per bit decreases, which is a little bit contradictory with what we had hoped we would be able to achieve, right? And just as an example, I've here listed, I mean, that's not from me, that's from the CEA. They have basically plotted on a graph different radio systems that were optimized for power consumption as a function of their data rate. And as you can see, as the data rate increases, that goes to the right here, you see that there's a trend where the energy per bit, so the efficiency of the radio, gets better, which actually illustrates what I just said before. And if you take a Wi-Fi radio, for instance, that's actually much more energy per bit optimal than all these other radios. So actually, you would say, why not just put a Wi-Fi radio in my sensor? Now, that is obviously not possible for many reasons, like protocol reasons and peak power reasons. There are many problems that makes this Wi-Fi, and you don't need 50 megabit per second in those sensors anyway, right? So how can we try to optimize the radio such that we break this paradigm? And actually, if you look at it, it's not really, what you really need to optimize is the active time of the radio. What makes those high data rate radios very efficient is the fact that they are active for a short amount of time to send a certain amount of data, right? So if you could find a way, without changing the data rate, you could find a way to reduce the active time of the radio, then you've solved that problem. You've solved this energy per bit optimization problem. And that means that in this power consumption versus performance trade-off, we've figured out that UWB, ultra-wideband technology, was a very interesting technology to do that. And that's what I'm going to try to show you. Now, to talk about that, to make you understand what ultra-wideband technology is, I first have to make you remember how narrowband communication, the classical systems, operate today. Today, they operate with continuous waves. You probably all know that, with a certain frequency, which means that in the frequency domain, they have a single tone, and that's why they're called narrowband communication. Now, that was the type of communication that had been favored over the years because of the frequency diversity that allows multiple users to use different frequencies, right? So every user application has its own spectrum band. Now, as opposed to that, ultra-wideband communication doesn't use continuous wave, but uses pulses. Pulses to provide a communication. Now, in the frequency domain, a pulse signal in time has a large frequency content, as shown on the right part of the figure, which will obviously overlap with classical communication systems. So that's why the average power spectral, the average power spectral density needs to be much lower than narrowband communication systems, such that they don't jam other communication systems. So they operate at a very low power spectral density, which is usually below the background noise. So now, how can ultra-wideband in this pulse-based format solve this active time and reduce the active time of the radio? And that is very obvious. If communication is done via pulses, what you can think of, if you can make a radio that starts up and shut down only when a pulse needs to be transmitted, so active only when pulse needs to be transmitted, basically you have a radio which has a power consumption which is independent from the data rate. And that was actually what we were trying to achieve in our optimization. And that technique is called radio duty cycling. Now you have to think that those pulses are nanoseconds, have nanoseconds duration, which means that radios have to start up and shut down in nanoseconds, which was one of the big challenges that we faced in the design of those radios. But we've shown that that was possible. Now, a few words about the regulations around ultra-wideband. Ultra-wideband was licensed by the FCC in the early 2000, like 2001, I think. And they have defined a spectrum mask for ultra-wideband communication. They have to operate between 3 and 10 gigahertz, which means that an ultra-wideband signal can be a signal that occupies that entire spectrum mask. Now, there were some questions to the FCC, like how wide is an ultra-wideband signal? And there have been, I think, quite some lobbying behind that. And actually what the FCC has defined is that an ultra-wideband signal is defined to be a signal that has at least 500 megahertz of bandwidth, which is much less than the 7 gigahertz that is available there. Which means that that's very interesting, because even though it's ultra-wideband, it allows frequency diversity, which is interesting if in case of multiple users. So, which is, of course, very important in sensor networks. You have different sensors communicating probably at the same time. Right. So now that's for regulations. Now, recently, and when I talk about recently, that was about last year, there's a standard, an IEEE standard that has been released for ultra-wideband communication in the context of sensor networks. Now, they have a little bit deviated from the original example I've shown about ultra-wideband communication. Like, the top one is the classical way. You see different pulses being scanned regularly in time. What the standard proposes is, forces to systems to do is to concatenate the pulses into some sort of bursts, but keeping in a certain time frame the amount of pulses that are transmitted the same, which guarantees that the power spectral density is the same for both signals on top and the bottom. Now, just to give you some numbers, in this case, in the mandatory mode of the standard, the radio is active only for 3% of the time. Right? So I'm not going to give so much details. I don't think that's very relevant here. So we've been working on designing radio systems for ultra-wideband, and that was our transmitter. And actually, we were the first, and I guess we're still the first, who have published a 15.4a, so a standard compliant, IEEE standard compliant radio system. In this case, it's a transmitter in the world. So I haven't seen any other implementation, at least publicly available today. So that was a transmitter that was published last year at ISSCC. That's a chip microphotograph, and as you can see, the active part of the radio is very small. It's 220 by 300 micron, and actually all the rest of the area is consumed by the connectivity. So it's all those different paths that you see to communicate with the external world, which has defined the size of the chip, which means that there's a lot of work to be done in the integration of these chips in the complete system and a complete sensor system, and to optimize the connectivity between the different modules in the sensor. Okay, so that's just an example of the time domain output of these transmitters. So you can nicely see the different pulses being sent, and that's one burst. So, okay, a few words about the receiver. Actually, this is going to drive me into too many details. We've been doing, on top of the radio duty cycle in the receiver, we've also revisited a little bit the type of receiver architectures and come out with an optimal solution. There are different types of solutions. There's called analog correlation types of receivers. There's more classical receivers use digital correlation, and both of them have some power hungry, some of each of them have different power constraints, and what we've come out is an architecture that optimizes both the analog and the digital distribution of the different functionalities in the radios, such that it achieves an optimal power consumption. Right, so that was the full system that was developed. It's a complete receiver, including the A to D converters, and that's again the chip microphotograph. And as you can see, again, the active part of the radio, which is here on the right, occupies only about 1/3 of the chip. So everything is dominated by the connectivity. Now just a few words about the power consumption. So I've just compared state-of-the-art narrowband communication systems that are published today. Transmission is about 10 milliwatts, reception is 2 milliwatts. That's what classical systems do today with about a century of optimization of super heterodyne kind of receivers and transmitters. And ultra-wideband solutions, which is a very recent technology, it's about a few years of work. We've already been able to reduce the power consumption by 1 order of magnitude, and I'm sure there is room for improvement for at least to get at least 1 more order of magnitude, which is necessary for the power consumption budget that we had from scavenging resources. So there are other advantages for ultra-wideband. Like, for instance, positioning. It's an interesting feature of ultra-wideband, since signals are short in time. That allows a nice spatial resolution to position the transmitter with respect to the receiver by tracking the movement of the transmitter and measuring the time of arrival of those pulses. So there's some nice positioning capabilities for ultra-wideband. Also, security is an interesting. I just gave a few words here. In one of the previous slides, ultra-wideband communicates below the background noise. So basically, if you put an antenna connected to a spectrum analyzer and you have an ultra-wideband transmitter in the room, you won't see it, basically. That's why this type of communication has initially been done in a military context before. So now a few words about what's being done in the rest of the world. Actually, it's mainly research centers that are and universities that are working on that today. And this is just an example of what is being done in the MIT. They use a pretty similar concept as we do. So also using pulse-based ultra-wideband communication to do low-power radios. But in this case, they use proprietary kind of ultra-wideband communication interface. So they don't use the IEEE 802.15.4a as we do, which was a little bit striking to me because it brings the question: should sensor networks communication be standardized in the context of healthcare, for instance? And there are different pros and cons to that. Like, okay, the pros are obviously the interoperability, so you can add sensors very easily. Different manufacturers can design the same sensors and that can communicate with each other. There's market pressure that decreases the cost, but there's some cons, of course. There's the fact that in standardized solutions are not always power optimal. They're biased by the big ones. There's security reasons and interference. Okay, that's questionable. But I think standardization aspects in healthcare wireless systems is a subject of debate today. So as a conclusion, I would say that we've proven that ultra-wideband can offer at least 1 order of magnitude improvement in the power consumption in the radio. It has other interesting advantages such as security and positioning. There is an IEEE standard that exists today, but it's still a question whether this is something that can be interesting in healthcare applications. So that ends my talk, and I'll be open for questions after that. Thank you.